Dear students, welcome to this second chapter about digitalization or digitization. It's basically about the basics of everything, namely the bits in our computer. So first I would like to have a short discussion about this term digitalization versus digitization. Actually, is there a difference? This term have done a semantic shift. So in the 80s or 90s, digitalization has always meant to move from an analog representation to a digital representation. Today, the term digitalization is more used to emphasize the transformation of business models, or maybe the society based on digital computers. And to not mix it up, we have invented, or somebody has invented, a new term, digitization. And some people really distinguish between digitalization and digitization, and digitization has then the former meaning to transform analog data into digital data. And some others do not differentiate. And then you always have to ask what digitalization actually stands for. Today, within this lecture, we are talking about digitization. That is, we are talking how analog data can be represented in a digital way. We're talking about the digitization of characters, of numbers, of pictures, and of audio. To make things a little bit more complicated, especially for the German students, the terms digitization and digitalization are used in the English or American countries. However, in Germany, two other terms have been used. So digitalization is nowadays the term for moving from analog to digital data, and digital transformation is more the one where you have a transformation of business model, and so on. This lecture today is about digitization, so it's about moving from analog representation to a digital one. Computers are based on digital data. But what does digital actually mean? The term digital goes back to the Latin word digitus, which means finger. And if you maybe remember how you did count, or maybe even kindergarten or in first class, then you just used 1, 2, 3, 4, and you used your fingers to represent actually the numbers 1, 2, 3, and 4, and so on. And you haven't been able with the fingers to calculate, for example, 1.5 or 1/3 or something like that. So you have just discrete values, so just the numbers 1, 2, 3, and you have not the numbers in between. You have not these continuous values, but just discrete ones. And that's actually what analog and digital are, the differences. Have a look at the two clocks on the right side. The representation of the upper one is analog. So you have 3 pointers, one showing the seconds, and if you would observe very clearly, you could not only watch which second actually will be represented, but you could see tenths of a second or hundredths of a second. In the lower digital representation of the time, we just have 1300 hours and 26 minutes, which is you have to wait, and once in a while it will move from 1326 to 1327, but there's nothing in between. There is no continuous times, there is only discrete time stamps which are represented. In a digital camera, something similar happens. You have continuous pictures, and while digitizing them, these are transformed into discrete values. Later on, we will have a look on it. Usually, the discrete values are represented by integer numbers, 1 to 3, 1,000, a million, something like that. And there are special cases for digital systems. One is a binary system. That means it's a digital system which only uses two values. There's an example, for example, the Morse alphabet. Two values are long and short, which are sometimes represented by a dash and a point. So if you would like to send an SOS, it's actually long, 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 short, 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 long, 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 or vice versa. So dash, 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 point, 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 dash, dash, dash. And again, we have a special binary system, which is a dual system, and this one has only two values, 0 and 1. Now, computers are based on digitalized data, are based on a dual systems data. So the first question is, why are computers digitized? And why do they use a dual system? Actually, there have been analog computers. However, these have not been successful. They are only useful in very special situations, and they are not something like a general computer which can be used for different kind of problems. And second, why do we have only a dual system, a system which is based on zeros and ones? Actually, it is simpler to just work with two values. So if you are look from an engineering perspective, you have, for example, magnetized and not magnetized. Or you have power and not power, or voltage or no voltage. If you would go for example, three values and a magnetized system, then you would have to go for magnetized, a little bit magnetized, not magnetized. And from an engineering perspective, this is very hard to implement. So two values from an engineering perspective are quite easy, and that's why we have nowadays dual systems and digital data. And once the computer scientists take over, independent of if you have magnetized or voltage or light or power, these two states are simply called 0 and 1. Probably you have already heard about that. Everything in a computer is based on zeros and ones. And actually, that's what I just tried to explain. And if I say everything, then it's really everything. Text based on characters, and these characters have to be represented by zeros and ones. So are numbers and pictures and audio. And nowadays there are even experiments with smell and taste and tactile information. Have a look at these videos in YouTube. And in the end, again, it's all based on zeros and ones. The smallest information unit is called a bit. So a bit is just some kind of memory which only can have a value 0 or 1. This is the smallest unit of information which exists. Less information is not possible. This 0 and 1 can here now interpreted in different situations. So if you have, for example, a traffic light, it could mean red or green. Or if you have just two sexes, it could mean 0 stands for male and 1 could stand for female. If you would like to have diverse sex as well, then 0 and 1 is not sufficient anymore. From a practical point of view, to handle a big number of bits is not manageable. Thus, 8 bits are packed together and called byte. A byte is now simply an information unit consisting of 8 bits. Question: why do we have 8 bits and call it a byte and not, for example, taken 10 bits? Usually, most things in our world are based on this decimal system, on the system based on the number 10. Actually, the reason why the computer scientists have chosen 8 bits to be a byte is that 8 is a number which can be formed as a 2 by the power of something, 2 by the power of 3 in this case. These numbers have really advantages. This 2 is basically these two values 0 and 1, and if you stay with the systems, there's lots of advantages. That's why computer scientists decided 8 byte, that is 2 by the power of 3 bits. That's why computer scientists argued 8 bits are 1 byte, so 2 by the power of 3 bits are 1 byte. Actually, 8-bit or 1 byte is still very little information, and it's just not manageable to handle big units of it. So specific bigger amount of bytes are used using this prefix kilo, mega and so on. But what is actually a kilo? Think about your real world experiences. A kilometer is 1,000 meter. A kilogram is 1,000 gram. A kilo euro are 1,000 euro, and so on and so on. And mega simply is 1,000 kilo or a million. And so giga is a billion, and so on and so on. Tera, peta, exa, and so on. Now this has a drawback, as 1,000 is not a number in the form of 2 by the power of something. And this has really, it has advantages in the computer. So computer scientists redefined the value of kilo. So kilo is 2 by the power of 10, which is 1024. So it's not that far away from 1,000. Mega is 2 by the power of 20, which is 1021 times 1021. A giga is 2 by the power of 30, and so on and so on. This leads to some problems or some irritations. So if you, for example, have a look on my memory, you can see this memory picture on the right side. So you see the detailed information is that there is 51 billion bytes, which seems to be 47.8 gigabyte. And this looks a little bit irritating. However, if you start using your table calculator, if you go and divide this 51 billion by 1024, and again by 1024, and once again about 1024, you will end up at these 47.8 gigabyte. So this irritation simply goes back to this usage of 1024 as our prefix value. So what you can see here is the relative fault between the two kilo definitions is small when you start looking at kilo, but it goes up for megabyte, gigabyte, and if you, for example, look at yottabyte, then the relative fault, the relative difference is already 20%. Anyhow, these values for kilo, they are established in computer science. And now it even gets a little bit more complex or a little bit more irritating. So if computer science talk, for example, the sizes of files and storage of media, then this is usually given in byte or kilobyte or megabyte or gigabyte. And here kilo and mega have this value 2 by the power of 10, 2 by the power of 20 and so on. However, when you have transmission, when you have bandwidth, so the capacity for sending data, then this is given in bits per second, not byte per second. And kilobit per second, megabit per second. And here the factor kilo mega is still as used before. That means it's 1,000 or a million and so on and so on. So why that? The transmission of bits is part of communications engineering, which is a part of electrical engineering. It's not a part of computer science. Electrical engineers are using the classical definition of kilo and mega. And if you would want to run calculations like you can see on the next page, you have to take care for where do we use bit, where do we use byte. So you have to take care for this factor 8 between bit and byte. And you have to take the two different definitions of the factor kilo, mega, giga, and so on. So looking on this exercise, here really this type of problems pop up. So how much can now be expressed using bits and bytes? So let's start with simply 1 bit. And using 1 bit it is possible to define what we call 2 different states. So one state could be 0 and the other one is 1. Again, take this example of red and green in case of a traffic light, or power off, power on, for example, if you would like to switch a light on or off. With 2 bits, it is possible to define 4 states, namely the given one, 0, 0, 0, 1, 1, 0, 1, 1. With 3 bits, it is possible to define 8 states, 0, 0, 0 up to 1, 1, 1. They are listed in here. Generally speaking, with n bits, it is possible to define exactly 2 by the power of n states. Some of these 2 by the power of n numbers you should simply learn, because they pop up again and again and you're not irritated because some numbers might look arbitrarily chosen. So 8 bit, that means 1 byte. Here we have 2 by the power of 8 different states, which is 256. And now there is one more strange thing. For computer scientists, we always start counting with 0. So usually we would have, for example, when we talk about a byte, we would have 256 different states, and these are numbered through from 0, 1 to 255. But even if the highest number is 255, it is 256 different states. Now let's have a look. How many bits do we need in a given situation? So if you have a look on a traffic light for cars, then at least in Germany we have the following states. So if I show up as a traffic light, then it's usually red. And then it goes over to a status where we have red and yellow, and then red and yellow turn into green, and then we go back to yellow, and finally we have the initial state red. So in total there are 4 states of the traffic light. That is red, red, yellow, green and yellow. And now we could use simply 2 bits to represent these 4 different states. So for example, 0, 0 could be red, 0, 1 could be red, yellow, 1, 0 could be green, and 1, 1 could be yellow. Could have another example. How many characters does an alphabet have? Again, let's take the German alphabet. And if we only have a look at the small characters, then we have 26 characters. A, B, C, and so on up to Z. These are 26 characters. So how many bits do we need? If we have 4 bits, then 2 by the power of 4 is 16. That's not sufficient. Then we can only go up to something like p. If, however, we have 5 bits, then 2 by the power of 5 is 32. So it's a little bit more than we need. But in fact, we can't use 4.6 bits. We only can use either 4 or 5 bits. So in this case, we would use 5 bits. And there are some states which are not required. Now, how is this practically done? So if we do have now our 5 bits and we would like to have a bit presentation for each character, how do we do? And that's actually, from a technical point of view, quite simple. You simply create a table, and on the one hand you have these characters A, B, C up to Z, and on the other hand you simply assign a combination of 5 bits, and the only thing what you have to do is to see to that not 2 characters are assigned or related to the same combination. For example, if A and B both would be assigned to 0, 0, 0, 0, 0, and in the code there is suddenly a 0 for these 5 zeros, then you do not know if it is an A or a B. So it should be unique, yeah? But that's all. You can make it simple like I did it, so you simply count through and always add up one more bit. So the problem is actually more an organizational one. So how big is this table? So you have to know the number of characters you would like to work with in advance. And then you have to agree on a special kind of table which everybody is using. And this is not a problem which is easy to solve, and you can see this, you have experienced this probably before. So if you get an email and you have special characters in your country, like for example in German, the Ä, Ö, Ü, then sometimes it happens that these Ä, Ö, Ü are simply replaced by something else. And here some people have swapped these kind of tables, taken the wrong table, and this is what happens then. So these Ä, Ö, Ü are not represented in a correct way. There is one very popular representation of characters, which is the ASCII table. The ASCII table is actually quite old. So ASCII stands for American Standard Code for Information Interchange. It is a 7-bit table, so we can create or have representation for 2 by the power of 7, that is 128 characters. So what's in there? It's all American or British letters, small and capital, all digits, 0 to 9, some few special characters and some more. Let's have a look. So what you can see here is we have basically used this table or represented this table in 4 big columns, and each of these 4 big columns has basically 5 columns: decimal number, hexadecimal number, the octal number, and the character. So it's 4 columns, sorry. So let's have a look on the decimal number first. So it goes from 0 to 31 in the first big column, from 32 to 63 in the second big column, and so on, and it ends up at 127. So starting from 0 going up to 127, that's 128 different characters. Let's move to this 4th column. Yeah, in this first big column, you see you have special things like null, SOH, STX. We come later back to these ones. But looking on the 2nd column, you see that there is a character space, a quotation mark, you have a hashtag, and further down you have the digits 0, 1 to 9 and so on. And if you go to the 3rd column, you have this @ sign, the big capital A going to the capital Z, some more special signs, and in the last column you have the small characters A, B, C to Z, and again some more special signs. Actually, this ASCII table was designed for moving from typewriters to computers. And in typewriters, you do have special keys. For example, you have this key number 13, CR, carriage return, which brings back the carriage from right to left. Or you have this thing on 10, digital 10, LF line feed. So you move up the paper a little bit to the next line. So all these characters in the first big column, these are special orders on these typewriters. So what is the disadvantage of this ASCII table? So if, for example, you would like to go for a German text, then you do not have these letters Ä, Ö, Ü. And if you go for a French one, you do have these letters A, for example, with an accent grave, accent circumflex, accent aigu, and so on and so on. So quite many countries do have, quite many languages do have special characters. So first attempt would be to maybe have these less important characters in ASCII redefined by national characters. And here you come up with compatibility problems. So if somebody from the US sends a letter to German, it would probably fail. And the second attempt could be to enlarge the table. For example, we say we do not have 7 but 8 bits, so we come up to 256 characters. And the first 128 characters we leave as they are, and the second 128 characters are different in each country version, let's say. But even if you double the table in size, which would not be sufficient in the long run, if you think, for example, of the Arabic or Greek or Cyrillic or even the Chinese alphabets, then we simply have much too much characters. So what's the way out? Basically, there is one alphabet or one table which is used nowadays, which is called Unicode. And Unicode has two very good characteristics. The first is the first part of Unicode is simply the same as ASCII. That makes it backwards compatible. And the other good characteristic is it's extendable. So the table can grow and grow if more languages have to be included. Nowadays, all known characters from basically each language on the world is included. So the Latin alphabet, the Cyrillic, the Chinese, there's a lot of Indian alphabets, but even Egypt hieroglyphs or cuneiforms. And on proposal for the fans of for Star Trek, there is Klingonian alphabet, and if you prefer the Lord of the Rings, then Albion maybe is an option for the future. So how it is done? There are 70 planes consisting of 16 bits, but again the table is extendable, so you can have more than 60 bits. And nowadays most of our applications or most of our character-based applications are based on Unicode. You can see this, for example, in PowerPoint or Word or Excel. If you would like to include a symbol, then you can type it in and always the Unicode is given. And actually you can go in the World Wide Web to the Unicode code-table.com page, and you can find here all different kind of codes. For example, all emojis which are nowadays used in WhatsApp, Instagram and co. These are also defined in this Unicode table. Now let's have a look how numbers can be represented with just zeros and ones. So our normal numbers are based on 10 digits. That's why we call it a decimal system. The decimal system is a denomination number system, in German Stellenwertsystem. That means the value of each digit depends on its position. And let's first have a look on decimal numbers. Here's a given example, and you're so much used to it that you do not have to think about it anymore. But what does it stand for? So the 3 at the very end, it's at the position of ones. So it basically means we have 3 times the value 1, which is 10 by the power of 0. Then the 2 means we have 2 times the value 10. Yeah, and the 10 is the value of this position, which is 10 by the power of 1. And the first 1 stands for these hundreds, which means we have 1 times the value 100, and 100 is 10 times by 10 by the power of 2. So basically the value coming from the back is 10 by the power of 0, 10 by the power of 1, 10 by the power of 2. If you would have one more value, it would be 10 by the power of 3, namely it would be the thousands. And simply looking on this decimal system, the idea how to create dual numbers which are just based on 2 numbers, 2 digits, namely 0 and 1, becomes quite obvious. So here we have a number 1011, which is a dual number, and the last digit is now 1 times 1, which is 2 by the power of 0. The second last one is multiplied with the value of this position, which is 2 by the power of 1. And then we have this 2 by the power of 2, which is 4, one position before. And the first of these 4 positions is then 1 times 2 by the power of 3. So coming from the back, we have these position values of 1, 2, 4, 8. And we would have 16, 32, and so on before. So that's basically all. And of course you would like not to simply create this type of numbers, you would like to work with these numbers, you would like to calculate with these numbers. And actually this is as easy or as complicated, if you don't like math, to do. You can do it as easily with dual numbers as with decimal numbers. However, we will not emphasize on this topic in this lecture. Dual numbers can easily be transformed into decimal numbers and vice versa. And again, I don't go into this issue. And then you know there's more than positive integer numbers. So it's not just 0, 1, 2, 3, 4. There is fractional numbers like 1.5, or there are negative numbers, and so on and so on. And again, I won't touch it in here. However, there is one point I would like to mention, because we just have the dual system. However, in computer, or sometimes if you would like to represent the dual numbers to the outside, then hexadecimal numbers are used. Dual numbers tend to become very long, so you need quite some digits, 10 digits, 20 digits, simply to represent numbers which are used. And then hexadecimal numbers have an advantage. Let's have a look on the following table. So here you can see a decimal number in the column, first column 0, 1 up to 17. And you have the binary representation of it. And these binaries I have done in blocks of 4 digits. So we have 0, 0, 0, 0 for the decimal 0, 0, 0, 0, 1 for the 1, and we go up to 1, 1, 1, 1 for the 15. You can simply check 1, 1, 1, 1 is 8 plus 4 plus 2 plus 1, which is simply 15. And once you have reached these 4 ones, you have to add one more digit. Yeah, so we go to 2 blocks of 4 bits, which is 0, 0, 0, 1 and then 0, 0, 0, 0. If you have hexadecimal numbers on top, we have a system based on 16 different digits. So we start with 0, and if you come to 9, we have to simply have 6 more digits, and these are A, B, C, D, and E and F. And you can see simply that each of these hexadecimal digits corresponds to one block of 4 digits, of 4 binary digits. So F is this 1, 1, 1, 1. E is this 3 times a 1, then a 0. And if you have this hexadecimal 1, 0, again we have this 00001 in binary followed by 4 O's, by 4 zeros. As each of these 4 digits in binary exactly matches to one hexadecimal digit, it makes it quite easy to transfer binary numbers to hexadecimal numbers. That's why you sometimes see numbers in hexadecimal form. So don't get irritated if you see a number like 982B. It's simply a number in hexadecimal form and can be easily transferred into a decimal number. It's no magic, it's no mystery, it's simply a hexadecimal number. Most calculators support the transformation or the calculation of the numbers. However, you have to go into a programmer's mode. If you have the Windows calculator, then you simply in the options can choose programmer and you can calculate with hexadecimal, decimal, octal or binary numbers. And octal just use 8 digits. And the same is for the calculator on the Mac. Now let's move to pictures and how pictures are represented by zeros and ones, by bits and by bytes. It's actually a little bit more complex. Pictures are continuous, that means they're analog in 2 respects and thus have to be digitized twofold. The first is the color scheme. Actually, we have lots of continuous colors. So if you move from blue to red, there are millions and millions colors in between. And there's no way in the natural world to just say we have 10 or 20 different colors in here. But actually we have to map all these colors to a discrete color scheme. The second thing is we have a geometry of the picture, and this is continuous as well. So if you have a picture of let's say 10 centimeter times 10 centimeter, you can identify spots and make these spots smaller and smaller and smaller, so it's continuous. And here we have to come up with a discrete matrix as well. So how does it go? The geometry first, a picture is divided up in so-called pixels, which is an abbreviation for picture element. In digitized pictures, each pixel is an atomic point in the picture which has exactly one color assigned to. Usually pixels are organized into rows and columns. And when you look at colors, the easiest way to define a color table is like to handle it with characters. Each color is represented by a number, which is a combination of bits, and the number of colors, that means the color depth, determines the number of required bits. There is different standards. One very commonly used is the RGB standard, which is a little bit more complex. So what does RGB stand for? Actually, it means red, green and blue. And for each component, for example red or blue, 1 byte is used. So 1 byte, again 2 by the power of 8, 1 byte 8 bit, 2 by the power of 8. Here we have 256 different values starting from 0 going up to 255. And as we have these 3 different basic colors, R, G and B, we have 3 bytes, which means we can compose roughly 16 million colors in this way. Let's take an example. Here on the on the right, you see a picture. This picture is already a digital picture, as you can see it on your computer. However, for the time being, let's pretend it would be an analog picture. So how can we do to make it digital? So the first thing what we have to do is we have to create a grid to define the pixel. Yeah, so what I'm doing here is I have this 215 times 202 pixels, which use, oh sorry, in the original we have 250 times 202 pixels, which use 45,000 different colors. Now I have used a new grid. Yeah? And what do I have to do? If I take a closer look on one of these pixels, you see each of these pixels is still complex. Take for example the upper right pixel, which has a green triangle in the upper left corner, some yellow triangle in the lower right corner, and some black diagonal. So there's lots of colors, but a pixel can only contain one color. So what we have to do is somehow to create an average value for each pixel. That's what I've done in the next step. Oh, sorry, it's the wrong direction here. It is. And you can directly see by creating these pixels, information is lost. The quality of the picture is becoming worse. So we have less information in our picture. So I've done this. So the grid made created 40 times 50 pixels, which is 2000 pixels. Actually, you can see I've numbered it through. There is still 1940 colors, meaning we have actually for each pixel a different color in this picture here. Now I would like to assign it to only 16 colors. That means I would offer 4 bits per color. And this shown scheme in here is not the one which is later on used. So we take another one. But the picture becomes even worse in quality. Now I have a picture with 50 times 40 pixels, which only uses 16 colors. So what can we say? So if you digitize a picture, there's always a loss of quality. Maybe as our eyes and our brain are not precise enough, we cannot see actually this loss of quality, but in fact there is. If you, for example, enlarge a picture, so we make it bigger and bigger and bigger, a digital picture, and you can see here I have done it 32 times, so I have now each pixel is 30 times larger than its original. Then you can suddenly identify each pixel. And you see it is not continuous anymore, it simply looks like a mosaic. Let's have a look on the color schemes. On the left side you see, I think it's a sub window from PowerPoint, and you can see this current color in the table on the left. Then you have this RGB, red, green and blue. And you can see the currently chosen color has a red value of 156, a green value of 155 and a blue value of 178. And of course you can simply define these numbers by yourself. You see this HTML code here as well. So it's 9C, 9A, B2, and this 9C simply corresponds to 156. This 9A corresponds to 154, and this B2 corresponds to 178. So this HTML code in hexadecimal is much easier to read and to copy and so on compared to a binary number. On the sub window on the right, you can see that you can choose several resolutions for your screen. And here 1280 times 800 pixels is chosen, and the color scheme uses 32 bits. This depends of course on your monitor, on your computer, and of course the higher the resolution, that means the more number of pixels, and the higher this color depth, the better is the quality of your picture. But on the other hand, you have a trade-off. You need more memory space, or if you would like to transfer the picture, it simply takes longer time. Again, let's have a look on this RGB color scheme. You see 0, 0, 0, 0, 0 stands for black. So if there is no red, nor green, nor blue, then simply no color is transported, which means it's black. And the opposite would be FF, FF, FF. So both or all red, green and blue are powered up to its maximum. Then you have white. And if you simply go, for example, for FF 0000, means red is at its maximum and both green and blue are at minimum, then you simply have a red color. Same for 00, FF 00 and so on. Like we had ASCII, we of course do have different standards for the resolution of pictures. For example, for the analog picture, we had pixels as well in the video recorders, which is VHS. It's 3020 times 240 pixels. DVDs typically have 270 times 576. We have HD TV, we have VGA, SXGA, we have HD, 4HD, and so on and so on. So there are lots of resolution which are standardized. On this graphic, on the diagram on the right, you see some diagonals, and these diagonals represent these relation 16 to 10 or 16 to 9 or 4 to 3 of the horizontal or in the vertical of a monitor. Finally, let's have a look on audio. Sounds, music and noise are all represented using sound waves. And sound waves can be digitized as follows. In defined intervals, the value of the sound wave is measured. For example, every 10 times per second. And the measured value will be mapped to a given scale. Actually, this can be shown in a diagram, and you have maybe seen oscillographs before, which make a picture of the sound. You can see a picture down here on the right side. So the idea is in principle quite similar to the digitization of pictures. The frequency of measurement is similar to the resolution of the picture, so the organizing a picture into pixels, and mapping the measurements to a given scale is similar to the usage of predefined color schemes in pictures. Let's have a look on concrete examples. What you can see here is 3 pictures. In picture A you see a sound wave, and in picture B you see the sampling of the sound wave. So each of these vertical lines represents a measurement which actually is at this given time at this sound wave on the left side. And what you can see here already is the more measurements you have, the more measurements you make per time period, the better you can identify this original wave. If, for example, there is a dip between 2 lines, you would not be able to see it. If you go from B to C, you can see that there is lines only in predefined values. What you can see directly is that these shape of these lines are not as good representing this original sound wave as the second one did. Taking these measurements is called sampling of the sound wave, and this step B to C is called a quantification of the samples. Here these measurements are mapped to a given scale. And as we did for monitors or pictures, we have predefined standards. For example, in the telephone, we use a standard called pulse code modulation. This is based on 8,000 8-bit samples in Europe per second. Which means, due to an electrical engineering, acoustic frequencies higher than 4 kHz are lost. And again, you have the same effect as with the pictures. Sampling and quantification always means that you reduce the quality of the audio file. The more samples you have per second and the more bits you have per sample, the better the sound is. However, there's a trade-off. If you use more samples and more bits, then you have to have more memory and or higher transmission capacities. So it's a trade-off between quality and costs.